Hello, and welcome to the Analog Devices Precision Training video that focuses on precision digital to analog converter technology. This video will go through total unadjusted error specification, also known as TUE, and how this relates to digital to analog converters. Discussed are the key differences that exist between the TUE datasheet specification when compared with a calculated TUE value. We will highlight the advantages that the TUE specification offers when considered as part of the error source calculations for your design. Many people, when designing their solution, take the worst-case accuracy specification as the TUE, and this is the correct approach. By using this value, they are effectively taking the worst-case value that the actual DAC output value can be from the ideal value at any given DAC code setting. For this, it is assumed that a perfect voltage reference is used. As stated in the previous video on static errors, when a DAC is programmed with a particular value, the corresponding DAC output is loaded with a value that is slightly different to the expected value. This deviation between the programmed and loaded values occurs due to DAC errors that must be accounted for. To calculate the actual DAC output value, the TUE specification must be used. However, in the absence of a TUE specification, the worst-case error can be calculated using the formula shown. Here, it can be seen that this worst-case error takes into account the integral nonlinearity, or INL, offset, and gain errors are zero-scale and full-scale errors. It should be noted that the formula highlighted here does not take into account that the worst-case maximum specification of each error component may not have been measured at the same condition. Thus, this could lead to a worst-case error calculation that may look a lot worse than the actual specification really is. A total unadjusted error is the error measured when all potential sources of error are combined into a single specification. This takes into account the variability of individual worst-case sources of error. Let us look at an example. Here we will go through the calculation of the TUE for a DAC, where we take the individual error sources and compare with the measured TUE datasheet specification. Here we show the ideal unipolar transfer function of a DAC, where the analog output range goes from 0 to positive full scale. Looking at the error sources and their worst-case specified values, the INL error, the offset error, and the gain error. These are used to calculate the worst-case accuracy error. As mentioned previously, the worst-case gain, offset, and linearity errors will not usually take place at the same measurement condition. When measuring the actual output from a DAC, if we consider temperature and its effects on the error sources just highlighted, some may be affected while others may not be. Taking an example of where the TUE is calculated from the worst-case error measurement values recorded across temperature, this also takes into account the errors that are introduced by manufacturing process and operating parameters such as supply voltage. Here we see TUE gives a far better indication of the device performance over taking the worst-case maximum error sources and calculating from these. To learn more about Precision DAC's static errors, please continue to watch our video on the DAC Error Budget Calculator tool in our DAC Precision Training series. Click on the link below or go to Analog Devices Precision Digital to Analog Converter landing page.